Today we are going to start on cellular networks. Now the cellular networks could be a class, a whole course by itself, and there are universities where they teach a whole course on telecommunications networks. We are going to try to do it in 2 lectures, actually 1G, 2G, 3G in 2 lectures, then 4G and 5G in 2-3 lectures. So basically we have very few lectures. So this is a concentrated version of telecommunication networks. We'll talk about how the cellular telephony started, how they use the frequency again and again. Then one of the very common standards I couldn't escape is GSM. GSM is 2G, but it is used worldwide, including here. And if you have a phone right now, very likely it is a GSM phone. So GSM, we have to talk about that. Then we talk about GPRS, Edge, and 3G, W-CDMA, and HSPA. And after that, we move on to 4G in the next lecture. So basically, back in 1970s, AT&T, when it was still one company, monopoly, developed a plan that they could provide radio services to the whole country using this plan, where if they are given 7 frequency bands, they could use it again and again and again using hexagonal cells. Okay, so they would put 1 here and then 6 around it, and then 1 here and 6 around it. So what will happen is no 2 frequencies in the adjacent zone would be same. You see, so 3 and 6, 1 and 2. So there won't be edge effect, right? Interference. So this is basically in 1977, then FCC said, okay, let's begin. And they said, of course, by that time, people were already talking about breaking up AT&T. It was a monopoly then. And so they said, we will give it to 2 companies, one AT&T Bell, and one to something which is not a Bell. And so American Radio Telephone Service, and both services started in 1983. All right, just for experimentation. Then, finally, when everything seemed to be working, then they said, okay, all right, we will go countrywide. And they divided the country into areas. And 2 kinds of areas, metropolitan areas and the rural areas. Metropolitan areas are the densely populated like St. Louis. Rural areas is if you go just 100 miles from St. Louis. Okay? And so 75% of the US population lives in the metropolitan areas, and that covers only 20% of the US area. Right? It's like 80-20 rule. Right? And that was divided into 306 areas, MSA. MSA is the Metropolitan Service Areas. Then 428 Rural Service Areas, RSAs. These basically were larger cell sizes. Okay? Now the area is bigger, population is less, you make less money, so not everybody wants to go there. Everybody wants to go into the Manhattan downtown where there are millions of people, rich people, as opposed to, here, right? So the area was divided into this, and everybody had to basically kind of petition for that area. And then they said, we won't give it to one company. In every area, we will give 2 carriers, A and B carriers. Okay? Incidentally, B stood for a bell. Okay, A and B, not A, B, C, D. B stood for a bell and A stood for alternate. Alright, so in every area there will be competition. 2 companies can offer services, A and B, and they said we will give you 832 channel pairs. So channel is 30 kilohertz. This is all came out from the experiment before, that we need 30 kilohertz to send 64 kilobit voice. The voice was 64 kilobit in those days. And so for 64 kilobit voice, they needed 30 kilohertz going down, 30 kilohertz going up, so that is channel pair. And they cannot use the same frequency for receive and transmit, so they had basically, two frequencies, one for down, one for up, 45 megahertz apart. Okay, so they are far away so that the antennas will not get confused. Alright, so 832 channel pairs in each area, 416 per carrier, so half of the channel for this carrier, half of the channel for B carrier, 45 megahertz between transmit and receive frequency, 30 kilohertz per channel, and 1 to 7 frequency reuse with hexagonal cells. And they said, well, if I give this frequency to this one, then this, they were giving out different areas, right? So they, basically they planned it accordingly using hexagonal cells. By the way, all this is history because we don't use hexagonal cells anymore. Okay? And we don't use frequency division anymore. Right? This is the first version of the cell phone. And since the frequency was free, a lot of people applied for it. Right? And at that time they didn't realize that this is a money maker. So they gave it out free, and then finally when a lot of people applied, they started a lottery system. So if you're lucky, you get it. Alright? But anyway, they wanted to make sure that whoever won the lottery, they have to have at least one market in by 1990. If you didn't do it by 1990, then you lost your contract, and then you had to pay so much fine and this and that. So you cannot just go and apply for a thing and then you try to sell it to somebody else. Alright, so at least one system in every market by 1990. Any question about this history? Yeah.
What is lottery system? Lottery system. Why is it?
What kind of system?
Lottery system.
Lottery system. Why lottery system?
Why is it? What is lottery system?
Okay. Does anyone know why I said lottery system? Why lottery system? Huh?
Yeah.
Why?
Just so it's fair, I guess.
Yeah, right. Basically, the thing is, if there are 10 people wanting the same area, St. Louis, then who should the government give? So it is a random number, flipping. It's a flip a coin, right? And okay, all right, if head comes, you get it. If tail comes, you get it. That's the thing. So that's what it is, lottery system. So it's not that you have to buy a lottery ticket or anything, but basically, you probably have to buy a lottery ticket because you have to put a $10,000 deposit before you apply, right? And this is $1 million business. So all right, now the cell sites, they are being planned, and nobody wants the cell site in their area. Would you want? Actually, it is a big money maker. If you put a cell site in your home, you get a lot of money from the cell phone company. They pay you $500 a month or $1,000 a month. In fact, in the house in front of my house in India, there is a big tower. It looks so ugly. But more than ugly, I'm afraid that this will cause some kind of problem with all this power coming into, radiated into our house. But the guy is making money. Right? So he is happy. He doesn't know anything about the wireless or anything. He just, tower is there, right? So anyway, so nobody wants the tower. But what happens is they're everywhere. Okay? That's you don't see them. And they're hidden. So this is not a real tree. Okay, it's a tower. Okay? This is not a real, whatever that is, it's a tower. Okay? Similarly, this is water tank is a tower and this is a tower. So, this is how the cities are making money. This is how non-profit organizations are making money is by, just letting telephone company come in and, use the property. Alright? NIMBY, not in my backyard. Alright. And then what happens if you need a tower where, when there is suddenly a game or something, a big fair, then you get a cow. Okay? Cells on wheel. And they bring a truck with the whole tower in it. So now, actually it turns out the cells are no longer hexagonal, and they are no longer, frequency division will come later, but basically the size of the cells could be macro, micro, pico or femto. Macro cell is what we call a normal size cell, and it is generally a section of a city more than 1 kilometer radius. Micro is, so what is happening is because the number of users is growing and growing, one cell tower cannot sustain all of these 1 kilometer radius people. So they are putting more and more tower in the small areas, right? Those are called micros. Micros are less than 1 kilometer neighborhoods, and picos are busy public areas. If you go into mall, there are many cells inside the mall. Okay, every floor might be a cell. And so those are picos, and if you go inside a house, that's a femto. Okay? And femto cells actually, so femto cells. Actually, I do have one in my home. I was just thinking whether it is a femto or not. But I don't think it is femto. But basically what happens is, if you call your phone company and say that the signal is not very good, this and that, and if you're living in a suburb or something like that, where of course they don't have towers, then they will give you this thing which they have given me, is that you put near your window, it will receive the signal from the window and then broadcast inside the house. Okay? So the idea is it will cover the home. Some companies charge money for it, some companies give free. So I got it free. But basically, you can try with your phone company if you have a problem. So macro, micro, pico, and femto. Right? Everybody understand the need for it? Why we need them? Right? And the size. So the cell size does not have to be 6. Cluster size does not have to be 7. You could have cluster size of 4, cluster size of 7 that we saw, 19, and so on and so forth. Okay? So now mathematics comes in. So I got to play my academic part. So what if the cluster size is X? What is it that you get, right? So here it is. If you have radius R of the cell, and radius R, and you have n is the number of the cells in the repetition pattern, cluster size. Okay, so we already showed you 3 examples, n equal to 4, n equal to 7, n equal to 19. If n is the cluster size, d is the distance between the centers of the adjacent cells. So this is d is, if this is little r by 2 is the radius here, right? R is the radius itself, then d is the distance, little d is the distance between the centers of the 2 cells, and capital D is the distance between the centers of the cells which have the same frequency. So this is how far they are, right? So there is a formula for it. First of all, n is equal to, n must be I square plus j square plus ij. Take any value of I, take any value of j, put it in there. Whatever you get, those are the only feasible values of n. Okay? If you put I equal to 1 and j equal to 1, what do you get? 3. Right? So that is one possibility. And go on putting more and more. 2 plus 2 give you 4 plus 4, 8 plus 4, 12, so on and so forth. Anyway, somewhere you will get 7 too. I don't know what value is, but you will get 7, 4, 7 and 19 like we saw there, okay? So possible values are 1, 3, 4, 7, 9 and so on and so forth. So this is a series by itself. There's no name for this series. But the reuse ratio is that what is the distance between the ratios. So the radius is r and the distance is d. The reuse ratio is the square root of 3n. And so if you are given n, then you can take a square root of that, and that will tell you how far can you go times this cell radius. If you want to calculate the distance between the ratio of d and little d, that would be a square root of n. Now you can easily derive this with geometry. It's not that big a deal. But all I need you to know is that there is such a formula, and that you can use it. Yeah.
What's I?
What is capital R?
I.
I. Oh, I is any number, any integer, and j is any integer. So it says I is 0 through whatever number, 0, 1, 2, 3, 4, 5, and j is any number 0, 1, 2, 3, 4, 5. We put I and j some values, whatever comes out, that is the cluster size. N is the cluster size. So if you want a cluster size of 5, that is not possible. Okay? Only cluster size of 1, 3, 4, 7, and so on so are possible. And so the cluster size are always I square plus j square plus ij for some value of I and j. Okay? Okay, any other question? No question? Frequency reuse example. So here is an example that if the cell radius is 1 kilometer and the reuse factor is 12, what is the distance? So you are transmitting only in 1 kilometer. So after 6 kilometers, the same frequency will be used. Right? The same frequency will be reused after 6 kilometers. Capital D is 6 kilometer. And you get that 6 kilometer by this formula, square root of 3n. 3 times n is 12. Square root 36. Square root is easy, 6. Okay, so homework. What is the cell radius for a cluster size of 12? So here we are trying to figure out R given D. Just the opposite of the previous problem example. Easy. Now, so right nowadays we don't use frequency domain. We use OFDM and things like that, right? CDMA and OFDM and things like that, where we use a big band. We don't use 30 kilohertz channels anymore. So whatever you use, you get a band, and then you can use the same band in some other cell. But we don't use it in the same cell. In the same cell, we use multiple bands. We have sectors, right? So, if you assume that you have 3 sectors and you're going to use 3 different frequencies, so one actually different frequency in each sector, right? And your cluster is size is 1. So basically you're going to just use the same in every cell. So you're not going to use cluster size 7 or any. Cluster size is 1. So this is what the picture looks like. So you see here I'm using red frequency, green frequency, blue frequency. In the next sector I'm not using red or blue, I'm using green. Why? So that it doesn't interfere with that other cell. Okay? So the sectors are arranged such that they don't affect the nearby sectors. Okay? So if you calculate the number of cells per cluster and number of sectors per cell and number of frequencies per cell, that is the number you specify, n times s times k. So when you say, well, in St. Louis near Bashu, we are using 1 by 3 by 3, which means we are going to use just one, in every cell we are going to repeat it. Okay? and we are going to use, next thing is S. We are going to use 3 sectors. It could be, any number of sectors. It doesn't have to be 3, and there is no mathematical formula as how many sectors you can use. You can use 4, you can use 5, you can use 6, you can use 12. As many antennas you can put, you can have the sector. Alright, so 1 times 3 times 3 means that I am using 3 sectors, and then I am using 3 frequencies, so that's easy. Then I use 1 frequency per sector. Okay? And by the way, this looks very nice picture, but in the real world, these pictures are not square or hexagon or anything like that. They have to do a survey, because the hills, and there are things which will mean that your sector cannot go as far as you want it to go. It will go somewhere less in a hilly area and more in an open area, and with trees it will go less. So they really have to do a survey and then decide, where to put the towers. Okay? So the actual map is very, very ugly. Any questions about this? Yeah.
In the picture that is shown, where is the sectors and
it is what?
the sectors basically? In the picture that is
Uh-huh.
I mean, the K is shown.
K is shown.
Which are,
K is the number of frequency allocations.
which are
Yeah.
the red,
Yeah.
whatever.
Yeah, actually what you are saying is right. Basically I was thinking the same thing, is that shouldn't they tell me that I'm using 1 frequency per sector rather than 3 frequencies in the cell and 3 sectors in the cell? Which is indirect way of saying that one, normally you would do that, right? And having said that, again, this is not really, I could use 2 frequencies in 1 sector and 1 frequency in the other sector, so it is not has to be evenly divided. Things are much more complicated in the real world. Basically, if you are facing Washu, most of the people are in the Washu, and then the other side there's nothing. You might have more frequencies on this side than the other side, right? So things are more complicated. But for the time being, for simplicity, we are showing you some things. And by the way, this is something that is real too. So I worked with WiMAX Forum for 4 years. Some of this knowledge I gained there actually. So the people are talking about, we have this frequency 1 by 3 by 3, and I'm thinking, what is 1 by 3 by 3? So I'm just giving you that knowledge back here. That, if you go in the real world, they will talk about like this, and you have to know what it is, what they are talking about. Alright, here are other ones. 1 by 3 by 1. So we are going to use the same frequency in every sector, but I'm going to have 3 sectors. Or 1 by 3 by 3, in which I will have, this is the previous one anyway, 1 by 1 by 1, where I'm just going to use same frequency. Now, in this picture, I have also shown what they call SS, subscriber station. Alright? So subscriber station is going to get, if you have this kind of thing where 1 by 1 by 1, they're going to get, how many signals are they going to get? They're going to get a lot of signals. They're going to get a signal from their tower, and from the nearby tower, and from the tower over there, right? So there will be a lot of interference. So what you do is you design your frequency pattern, your transmission pattern. Now they are designing antennas such that this signal will be very weak by the time it crosses that boundary. Okay, and you can do that. Alright, so the thing is, even though they are the same frequency in each cell, the subscriber station at the boundary will have some problem, because they will get from this and that at the same time, same thing. And so then we discussed as to how to handle those subscribers. Okay, but most of the other people will get one strong signal, and that is what they will lock on to. Okay, 3 by 1 by 1, 3 by 3 by 1, and 3 by 3 by 3. Alright, please look at all of these if you have any question about any of these. Yeah. Yeah. So here, this the cluster size is 3. Right, the first number, right? The cluster size is 3. So you see this is 4, 5, 6, and the 4, 5, 6 happens here again. Not anywhere around it. Right? And so 1, 2, 3 happens here and 1, 2, 3 happens there, right? So the cluster size is 1, 2, 3, 4, 5, 6 and 7, 8, 9. Those are 3 clusters. And then we repeat some kind of thing. So 3 cells in a cluster, 3 sectors in a cell, and 3 frequencies per cell. Yeah.
What you just explained, is it the sector or the
I know. What you are saying is the cluster doesn't look like a circle to you, it's a line.
I mean, no. Cluster basically, what it means is that in the same...
Yeah, so these 3 are same. Basically, we are repeating this. Okay, I'll let maybe your second question. 4, 5, 1, 2, 7, 8, 9. There might be 4, 5, 1, 2, 7, 8, 9 here. 7, 8, 9, 4, 5, 1, 2. Just repeating that kind of thing. They are repeating that kind. Is that the question? No, I didn't get the question yet. Okay, what is the question?
What you just said is basically the cluster itself relating to the whole Higgs cell.
A cluster is this. No, hold on. First of all, you have to understand what is a cluster. Cluster is this. Repeating pattern, right? This is a cluster, right? I mean, if you go back to even first slide, this is a cluster. Blue thing is a cluster. Okay? Alright. Now, it doesn't stop right there too, is because now, with the current antenna design, we can do something at the edges different from the center. So you could use 3 frequency inside the center in a cell and then use F1 at the edge. Okay, 3 inside the cell and F2 at the edge, and 3 inside the cell and F3 at the edge. So basically at the edge there is no confusion, in the center there is no confusion anyway. Right? So, I mean, now the antenna design and the cell design is becoming more and more complicated, but there is a name for this. This is called fractional frequency reuse. Fractional difference. So inside a cell, different fractions of the cell, actually generally the boundary and the edge and the core have different frequency pattern. It's the same tower, one tower though, right, in the cell. Yeah.
What's the advantage of doing that?
Oh, advantage. So basically in this case the problem was that the edge guide, the people who are here on the edge, they get exactly the same strength signal from both the towers. And that causes some confusion, sometimes they lock onto this one, sometimes they lock onto that one, they might be oscillating. Right? So in this one that problem is not there.
On that previous slide, is the frequency reuse marked on there at all?
Frequencies are marked. The numbers are the frequencies.
Oh yeah, okay, I see.
Right? Inside the cell there is a small number, that is the frequency. Alright, fractional frequency reuse. So this is the homework for you, and I will let you think about it. Go on to cellular telephony. So cellular telephony goes by the G's. G stands for generations. The first generation 1G, 2G, 2.5G, 3G, 3.5G, 4G. Right now we have 4G, 5G is coming. Right? So the 1G was started from the North America, amps. Okay? And of course the Europe is different. They started with TACS, PACS, and then quickly people moved on to second generation, and so on and so forth. The main differentiator between the generation is the technology and the workload. So the first generation was all analog. So they didn't, you take your voice and your waveform looks like this, they transmitted that waveform, not zeros and ones. Okay, that waveform was transmitted onto a radio wave, on a sine wave, and demodulated at the other end and played back. That would be analog transmission. And obviously it only for voice. Basically, of course, data you cannot transmit like that. So, and they didn't even think about the data at that time. So the analog, the 1G was analog and FDMA. Frequency division multiple access. So everybody got a different frequency. So if I am talking on the phone, when I talk, I tell on the control channel to this cell tower that I want to talk. They will say, okay, I'll go on to channel number 433. Then I transmit on 433. And of course, 433 also has a reception, corresponding reception channel, because there you get two channels, right? The channel pair. So you talk on this and receive on this. And then when you went away, then somebody else got 433. So that was the way 1G worked. And pretty soon they realized that this is not the most efficient use of the spectrum or the best way to send voice. So they became digital. What does it digital mean? That instead of sending the wave pattern, they digitize the wave pattern. So at every point they measure how high, and made it a number and sent that number. Binary number. Right? At the other end, they got the number and made a square waveform, which after smoothing became very similar to what it was in the beginning. I like the digital. So that is 2G. It's still voice though. And then they started getting they started feeling need for data. So then they started updating, and so they came with voice plus data, 2.5G, more data in 3G, and so on and so forth. And 4G is almost all data, and 5G is 100% data. Voice is just a noise. Okay? So, as you can notice, the other thing it says is that this was FDMA, this was TDMA and CDMA. 3G was all CDMA, and 4G is all FDMA. Yeah.
What's the? I'm not sure what the difference between the voice and the data is.
Okay. So, what is the difference with voice and data? Two big differences. First of all, data is not in a hurry. Right? Voice has to reach there within, whatever microsecond, millisecond there. If something got out of order, you lost it. Right? So data can wait. Voice cannot wait. Right? Second thing is the bulk. Data is so big, voice is so little.
Isn't 4G still is that not used for voice too?
Yeah, right. So thing is, here's the thing. When you previously, if you go back, well, even now they're trying to do it. Previously, they used to charge you for how many minutes you talked. Now they don't charge you for the minutes. They charge you for kilobytes and megabytes. And then you get 100% all you can talk. Because all you can talk, if you talk for the whole month, it would be so little. As compared to the data, if you send 2 files, you are done. You watch 2 movies, you are done.
So the representation is not changed?
Volume. So the thing is, so the voice is, here is another thing. Voice was very quality of service sensitive in the beginning. Now what people have done is they have made ways of transmitting voice over normal IP networks such that even with some delays it sounds okay. Okay? So it has become data. So voice can be sent almost like a data. So on the 4G when you talk, all they are doing is sending some packets from here to there, and probably giving a little bit priority to voice traffic because still voice is in a hurry.
It's reliable enough that it doesn't really have to differentiate between voice and other data.
Reliable enough?
I mean, like it doesn't have to
Well, that's another difference. I don't know if you are talking other things. So thing is, in the voice, if I say 7 and you heard 8, not a big deal. In the data, if I sent you $7,000 and you got 8,000, I would be very unhappy. So the voice is error resistant. I mean, error not acceptable. I mean, the thing is, with the voice, in fact, so basically in the voice, if you error rate could be higher, but the hurry it has to reach in time, right? Let me say another way too. So now voice writes the data train. Basically, the main train is data, and the voice is sitting somewhere there, right? In the previous days, when we used to have modems, have you used modem ever? Modem?
Yeah.
You don't remember. Maybe you were a child. In those days, the modem was basically you took the data and made it a voice and sent it over the voice line. So you took a digital number and make it sound like some voice waveform, modulated it, sent to the phone company, and then the thing was that this was the beginning, right? When the phone company was analog, the phone company became digital, but they did not provide the digital interface to the customer. So the customer still had this phone only. They take their phone, dial a number, and put it on the modem, and then they can connect, right? So that modem's job was to convert the data to voice, right? Nobody has used that. None of you have used that phone modem, right? So that is before your time. But basically, so what it was the main train was voice. The data was just somewhere, sometime. Now the paradigm has shifted. The main train is data. The voice is somewhere, sometime. Yeah.
Why international calls now charge by minute?
Huh?
Why international calls now charge by minute?
By minute. Yeah, that will go away. I mean, see here thing. I mean, let me tell you. This is all changing. I mean, I don't want to sell telephone company here right now, but there are phone companies that are offering plans which do not cost you minute. You just pay one time per year, international calls. And if you haven't looked into it, just look into it. And so these things are going away. All right, back to 4G. So several things. First of all, we are moving from voice to data, and from whatever the original phone company's protocols were, which we are not going to teach you here, to IP. Okay? And from, in the case of access, from FDMA to OFDMA. Alright? So you can see the trend as to how things are moving. And another trend was actually, and that was another thing which was constant pain, was that America was always different than Europe, or Europe was always different than America. And the reason was everything was invented in America. I'm sorry. Some people might object to that. Everything was invented in America, and by the time it went to Europe, they made it better. Alright, so they have a better system. Electricity. It started in America, 125 volt, 60 hertz. Now 60 is not a good number, and 125 is not a good number, but we got stuck with it because we started with it. By the time it reached Europe, they said, no, let's have the voltage 220 because then your current is less, your wires are thinner, and blah, blah, blah. Okay, so they got 220 volt system, and the rest of the world has 220 volt system. And 50 hertz is a better number than 60, and so on and so forth. And you go on to the television, same thing. Invented here, better over there. Telecommunication, invented here, better over there. So by the time it gets there, it is different and in some sense better. Yeah.
Just out of curiosity, do you know why phone plans are just so much cheaper in Europe?
What? Phone plans?
Yeah, data plans especially are maybe half the cost that they are. For example, like in Britain, everything's more expensive except the phone plans, which are like.
Okay, I don't know that, but basically, I think the plan, etc., mostly does with what the customer can afford. In India, it is 6 cents, 6 paise, which is like 1/10 of a cent or something. So how much customer can afford, right? So maybe their income level is low, or maybe people here make too much money. I don't know. All right, back to the technology here. So I just want to say that there are two trains you see here. This is European and this is American. Luckily for us, that coming here the trains collapsed basically. So now there is only one train going onwards, at least in the phone system. So you can use the same phone here and same phone there. Previously, there was no way to do that. And so the system in America, which was 2G, was based upon CDMA. And CDMA, by the way, is invention of Qualcomm, a company, an American company. And so it started here, CDMA. And there were other systems like TDMA systems and another digital lamps, which is again FDMA in digital. All of those went away. And CDMA became what they call EVDO and EVDV and so on and so forth, CDMA 2000. So here basically in North America, Qualcomm sold the technology called CDMA. Right? And you know what CDMA is, right? Code division multiple access. And then basically it reached Europe. So this third generation of Europe is all CDMA. Okay? And so second generation they had GSM, which actually was a good technology, again better than the American technology. So it went worldwide, GSM, and now it has come back to America. So Americans use GSM. AT&T is GSM. T-Mobile is GSM. The only company, and Verizon is CDMA still. Okay? So we have two systems. You cannot use phone from Verizon to AT&T, and so on and so forth right now. But so CDMA and so now in 3G, everybody is CDMA. The main difference is in 2G. So when you say Verizon versus AT&T, it's the 2G part that you cannot use. And the voice is mostly on 2G. So when you make a phone call, they still send you through the 2G system that they have. Okay? And that's why, the problem. If you just did the data, then maybe, it will be similar. But anyway, what happened was there were two organizations, 3GPP and 3GPP2. Third generation partnership project, and this third generation project partnership or something like that. 3GPP2 was for America and 3GPP for Europe and the rest of the world. And in the middle there is a fork here, China. This is the fork I was talking about earlier. So China decided not to go with the rest of the world, and they decided to go on TDS CDMA. And then finally they decided this was not good. So everybody had joined here to LTE. In fact, America was trying to do UMB, and they cancelled that and they joined LTE CAN. So now the whole world is LTE, moving to LTE advanced and then to 5G together. Okay. The networking industry tried to get into the game of the telephony, and so Intel took the lead and started the WiMAX. Okay, and WiMAX was the thing which was happening in 2009, and I was working with them from 2006 to 2009. That was the peak period of WiMAX. In 2009 it was done. Basically it was all technology was done, and there were trials and everything else. But then suddenly Qualcomm and other telephone companies, people came in and they said, no, we cannot take this technology. And they just took the technology and renamed it with small changes to LTE. Okay, so the Intel is out of business and Qualcomm is back in business, and we have LTE, which is the worldwide, which is very same as WiMAX. I can give you the lectures after lectures, very small differences. But the big differences are in the telephone company's own business, because this one is an evolution of their old 3G thing to 4G, whereas this one would have been a total replacement in some sense because it's coming from the networking industry. Right? So it didn't worry about any of the old legacy stuff. So that is the thing. This is evolution. And by the way, LTE, E is for evolution. And I don't know, this must be European English, that everything, when they say, next generation, instead of calling next generation, they say evolution. Okay? So, edge is an evolution, evolved edge, and then LTE is another evolution. Okay? So, that is their word for next generation. Alright. So, there are lots of acronyms on this. They're all explained at the end. I don't think it is worth going through the acronym because I don't have time to explain each of these right now. all I want to do is go into GSM, because that is the key, and everything else has kind of died. Right? And we will go into LTE later on, I mean after this, but I think that's mostly it, right? Alright, so just recapping. 1G was analog voice in terms of payload. FDMA, frequency division multiplex access, mostly 1980s. 2G, and by the way, these generations used to happen every 10 years. Telephone company, basically actually it could be 12 years or something like that, maybe even. So basically the ITU used to meet every 4 years. And so, okay, all right. They will work all through the 4 years, but every 4 years they will have a big meeting and they say, okay, this is the next generation of our telephony. So they used to tell 10 years every year, right? So anyway, 10 years. So 1980s was FDMA and this one. 1990s was 2G, digital voice, CDMA. And then there was some CDMA and other things. And GSM. And then 2.5G, because they couldn't wait for 10 years. So in 1995, they updated that and to all these other things, and which some of these we'll explain a little bit later on. And then 3G came out, which is all CDMA. So one thing about 3G is that whether it is Europe or here, everywhere it was CDMA, even though the European CDMA was different than our CDMA, I mean the American CDMA. And so but it was all CDMA. Okay? And now, I mean 3.5G is somewhat next year, and then 4G is all FDMA. Right? So WiMAX is there, but it is so little that I don't want to talk about it here now. So WiMAX was 3.9G, and then WiMAX 2 is 4G. And 5G would be 2020. Okay, so in 4 or 5 years, we will have the next generation. So, and you can see there is third trend too, is that the data rate is going up and up. So it might have been few kilobits in 2G, it was like 900, maybe 100 kilobits or something. And in 3G, it may have gone to 10 times that or something. Let's see. By right now in 4G, you can get up to 100 megabits, and if you have a very good system, you can maybe 1 gigabit. But here in 5G, we're talking about 100 gigabit and things like that. So, very high speed. Okay, so how we'll get there, and that is something. So the rate is going up, the access method is changing, and the payload is changing. Now 3.9 versus 4G, there is a lot of confusion, and actually confusion is now going away a little bit. But in 2009, basically nobody was sure what WiMAX is, what generation it is. So let me tell you some stories here. At that time, there was basically, WiMAX people said, okay, so ITU said, okay, we will have the 4th generation that will have these qualities. It will have 100 megabits and 1 gigabit per second to the user. Right? And WiMAX did not meet it. So they said, well, you cannot be 4G. And the second problem was that there was no spectrum. Every country gives a spectrum, and they say, okay, this spectrum is for 2G, this spectrum is for 3G, and so on and so forth, right? So what does WiMAX do? There is no spectrum for 4G, and there is no spectrum for WiMAX. So they said, okay, we are 3G. So they downgraded themselves to 3G. So I remember going to a meeting where they said, WiMAX is 3G, period. So now you got the spectrum. You go to any country, sir, I am deploying 3G. You got the spectrum. And then, of course, they're not 4G, and everybody wants 4G. So some companies started, and 3G is already there, which is much slower, right? So they started selling WiMAX as 4G. When LTE came, they were exactly same speed as WiMAX, same technology, same thing. So they call themselves as they started calling themselves as 4G. But they were not 4G. So then people said, no, they are 3.9G. Which is 4G, but not quite. And so the competition went on at ITU. ITU had put a whole set of requirements. If you meet these 10 requirements, then you are 4G. So they designed the next generation of their technology. WiMAX designed WiMAX 2. LTE designed LTE Advanced. And this is after my... I'm sorry, I stopped going to WiMAX in 2009. So between 2009 and 2000 whatever now, maybe 4 years after that, 2013, they developed WiMAX 2, which is 4G, which met all the requirements. Similarly, LTE developed LTE Advanced, which met all the requirements. So LTE Advanced is 4G. Now since LTE Advanced is all there everywhere, so now basically when you see a symbol 4G, you cannot be sure whether it is LTE or LTE Advanced. That's the thing. And somebody said that sometimes they say LTE. So they just don't, they want to be clear that this is, you think about whatever G you want to call it, it is there. This is LTE. Right? But really the 4G by definition of ITU is LTE Advanced.
But sometimes they show it like 4G.
Yeah, so then you are not sure what you are getting. You could be getting LTE. Alright? Or you could be getting LTE Advanced. So there is a lot of confusion there. And WiMAX forum is 3G and 3.9G as well, right? Actually, it is 3.9G to be sure. If there was a spectrum, they would never call themselves 3G. All right? So these are near 4G technologies. Going to GSM. GSM is a French name. And the French name was, I forget what it was. System Mobile, I remember. I think G was for, what is the global, I mean, I don't know what they call global in French. So, something like that, okay? So, basically, that is how it was named. And the reason it was French was, this is another interesting story, you won't find this in books, is because ITU is UNO, and they only recognize few languages, English, Spanish, French, something, I forget, whatever languages, right? And so most of the European work was done in French, not in other languages, French. And so this is GSM is actually, came through that at sea train to ITU. But anyway, so now it is called Global System for Mobile Communication. Global System for Mobile Communication stands for GSM. It is implemented in 90% of the cell phones worldwide, everywhere. And it is a 90 technology. So it is 25 years old, but it's still surviving. It is still there in your phone. If you have a phone without GSM, it doesn't go much anywhere, right? And it runs at every frequency that is available. 850 megahertz, 900 megahertz, 1800 megahertz, 1900 megahertz, and this is simply because every country gave a different frequency when the time came to give a frequency, right? I think 1800 is US, 1900 is UK, 900 is probably original, and so on and so forth. 850 is some other country. So quad band. If you really want to go worldwide, you have to buy a quad band phone. Okay? And otherwise you will find that your phone doesn't work in some countries. The biggest invention in GSM, and really a good invention, was that they separated the phone from the user. Okay? Previous to that, in the United States, even up until very few years ago, when you got a phone from the phone company, that was your phone. It was, your name was in the hardware right there. Okay? If I gave it to you, it is my phone you are using and I am being billed for it. So the phone and the users were like this. The GSM people said no. Phone and the user should be separate. So they put the user in a SIM card. That we call the card, right? SIM card is subscriber identity module. So that is where the whole thing about the subscriber is in that little card. If I take that card and put it into this phone, that becomes my phone. Okay, take this card and put it into that phone, that becomes my phone. You see, what convenient thing. We don't realize this today, but this was not the system in the United States. This was in Europe. In the United States, we got the phone from the phone company, and that was my phone. Okay, there was no SIM card. And so now basically everybody realized that this is a good system, so now it is everywhere. Yeah.
Nowadays they have integrated SIM card.
In the phone?
Yeah.
No, locked phone, you mean? No, they won't integrate in this. That will not work.
I mean, like Apple and Samsung now, they have like integrated SIM card inside the phone, and you just choose your company. That's it. Then you.
Okay, I will talk about that later. I haven't heard about that, and the thing is that would be going in the wrong direction. I think it is very convenient to have a SIM card and throw away the phone.
No, I mean you could switch it by moving the next phone and just subscribe. Just enter your username.
Okay, all right. So basically, it's quite possible that the SIM has gone into the cloud or something. So the idea is all the subscriber information is in that card. Okay, your name, your phone number, company, everything is in that SIM card. The phone will work with any SIM, and so you can buy any phone. And so that was the thing, SIM card. Now, FDMA, this was the generation 1. First generation was FDMA, so every frequency, once you are given that frequency, channel number 433, that was your frequency for as long as you kept the phone up. Right? And so that means we cannot use too many users. If there are 433 channels, means there are 433 users. So they said, no, that's not good. Let's give a piece at a time. So you do slotted stuff. Time. So this is TDMA. On each channel, the user is given a slot. So now, on the same 4 channels, I can use up to, 32 users. Right? And of course we will repeat. After 8 users, we will repeat again. So U1, U2, U3, U8, and then U1, U2, U3, U8. And so in that little time you get, because it is digital, that's the good thing. Because in the analog you cannot do that. In the analog, the waveform has to be sent, and the waveform is always this long, right? With digital, we can compress it, alright, send it at a higher speed or whatever, and then send it. So basically this slot is containing the voice that the user once said. No, actually this slot is containing the voice that the user once said in this whole time period. Right? In the whole time period, whatever you said, we get into digital a small packet and send it over. Right? So we can support many more users now. 8 times more users, just to be exact. And then this is the system that they designed. So the user equipment, your phone is called mobile equipment, ME. It has a SIM card, subscriber identity module. Your phone talks to the radio tower, which is called a base transceiver station, BTS, which is connected by a wire to base station controller called VSC. All the base station controllers are connected to a central office called Mobile Services Switching Center, MSC. In the MSC, they have several other things, including home location register HLR, visitor location register VLR, and equipment identity register EIR, and authentication center AUC. And then they are connected, that is connected with a very high speed line to the public switched telephone network, to the wired network. Alright, now all these acronyms, you got to remember them. Okay? Because we are going to use them left and right, left and right. SIM. Now, we don't have to tell you what SIM is, right? Same thing is ME, BTS, BSC, MSC, HLR, VLR, all of these. Now, so this is basically what they did was they put the radio part here. So this is the base transceiver station and most of the other logic here. So this is the BSC, and one controller can control many stations, many towers. right? And many controllers can be controlled from this central place. Now what is home? Actually, this is all in the next slide. So I'm going to go to the next slide. Page down. Come on. So one BTS. Oh, what did I do? Backspace. Okay. So I already said this. 1 BTS per cell. Come on. This is on a timer right now, so it will go back in 3 seconds, but I got to just keep it there. 23. All right. So 1 BTS per cell, 1 BSC can control multiple BSSs and allocate radio channels among BTSs. So then it can tell the tower what to do with what frequency, what user, all that map that you saw can come from BTS. Manages the call handoffs between the BTSs. When you go from one tower to the next tower, this controller knows that's happening. And control handset power levels. That's another thing, is that if you are near the tower, you don't want to blast 1 watt. When you are far away from the tower, you want to send 1 watt. As you come closer and closer, you send less and less. Otherwise, what will happen is the receiver will be overwhelmed by your big sound, and it will not hear other users. Understand? So people who are asking questions from far away, they have to speak louder, but people who are asking questions from close, they have to speak slower so that I can hear, because they're all talking at the same time. Right? So that's the reason. So there's a very good power control. Depending upon the user location, the power level changes. It is done same thing for the transmission, same thing for reception. So the transmitter, the base station changes its power, and then they ask you to change your power. Okay? All right, let's see. So all of this is done from the BTS, from the controller, BSC. And the mobile switching system connects to the PSTN. So that's another acronym we will use, PSTN, Public Switch Telephone Network, which means the wired network. And switches calls between the BSCs, provides mobile registration, location, authentication. So what are these things? So basically, you have registered with AT&T, or ENC has registered with with T-Mobile. So all of that information, basically, if you are registered with AT&T, and if this is AT&T's station, then it will say, okay, all right, this guy is okay, let him make a call. If you are not registered with AT&T, the AT&T MSC will say, no, this is not okay, they are not our partner, they don't have a roaming agreement with us, not okay. Right? So all that information is there in MSC. Now, how does MSC know? MSC keeps a home location register. Home location register is a registry of all people who are in St. Louis and registered with AT&T or T-Mobile, for that matter, into T-Mobile's SLR. And so their information is all there. They have signed up for video service. They have signed up for, this, that, whatever is all there in HLR. But when you are visiting Las Vegas, what happens there? Basically, over there, MSC will call the MSC over in St. Louis and say, we have a St. Louis guy here. What is he registered for? Can he make a phone call? Can he watch the video? So there is a VLR, Visitor Location Register. So HLR is your home, and VLR is all the people who are visiting St. Louis here, or in Las Vegas. VLR would be all the people who are visiting Las Vegas, right? And so that information will be good for a few days, because they don't want to, on every phone call you make, they don't want to call St. Louis. HLR and VLR. Clear? What is the authentication center? Can anybody guess? We have seen this before. Authentication center. Trust center. Yeah, this is where your certificate, your everything is. Basically is that. So this is where they keep all the security stuff and your password or whatever is required to identify you. And equipment identity register. That's another interesting thing, is that if a phone is stolen, it is in that register. So that phone has that this phone is good phone, this phone is a stolen phone, and so on and so forth. So when you make a phone call, that is checked here that, okay, this is a good phone. Okay. Now all of these are functions, again as I said before, and can be put into one box. So if you go to buy EIR, I don't think you'll find one in the market. Yeah.
So how does a phone get entered into the?
Oh, so there is a E whatever number when you were there's a number on the phone, right? So when you make a phone call, that number is transmitted along with your SIM information.
No, I guess how does a phone get registered and stolen?
Yeah, so the register gets stolen when you report it.
Oh, okay. You have to manually do that.
Yeah, right. Yeah. When you report it stolen, then it gets registered. Previously, I think it was very easy because previously you had every phone was phone company's phone and it was written in your name. Well, I mean, it was pre-SIM days. But anyway, similar technologies applied to the US system, but they were not so clear about the SIM and other business. But now, with this, I think this is becoming universal. All right. So, yeah, go ahead. Question.
How would the embassy in Vegas know that I'm from St. Louis?
Oh, your phone will tell them. See, the thing is, when your SIM card will have that information that this is Achinte Kumar from St. Louis and, customer number so and so. And so some information is already there, right? So your SIM is registered, right? And so that number, the SIM number itself will somehow tell them that you are from St. Louis. Unless they can find where to charge, they won't let you do anything. So believe it or not, by the time you get the dial tone, by the time you press something in dial tone, all this has been done. You won't get a dial tone until you have been authenticated and that your account is in good shape. If you didn't pay the bill for 10 months, you cannot make a call from Las Vegas. They will know. All right, home location, visitor location, EIR, authentication center. This is really painful. Oh, this is the number we were talking about, the phone number, IMEI number. That is the International Mobile Equipment Identity Number. That is like your MAC address. Right? It is much bigger than MAC address, but that's a big number, right? That every phone has a unique number.